We have completed our general introduction to mechanics with the last group of modules, and the next set of modules will be associated with solids, fluids, and waves that have special properties. And we're going to begin that with solids, and solids have the property of elasticity, which we're first going to discuss. So as we press on solids or stretch them, they are elastic, and we can elastically deform systems. When systems are generally distorted from equilibrium, the resulting force is proportional to the deformation. And this is called Hooke's law. So we're on section 11.1, and we're going to begin by looking at Hooke's law. Hooke's law states that the force that a system exerts on a mass is equal to a constant times the amount of displacement of the system from equilibrium. So for example, if we have a spring and there's a mass here, and this is the equilibrium point, so we'll call this x equals 0, then in fact if we take this mass over to another position, a distance x away, then in fact there will be a restoring force in the opposite direction that's indicated by the minus sign. So if x is in the plus direction, the force will be in the negative direction, and it will be proportional to how far I am from the equilibrium point. Likewise, if I take the mass and bring it over here and compress the spring, then in fact I'm a certain distance away here also, and in fact then, since x is negative, I have actually a minus x, the minus x times the minus sign gives a force in the positive direction. So this is the force that the spring is exerting on the system. And this is called Hooke's law. And it's a very important law. It's very important because it's a property of all systems near equilibrium. So if I take any solid near equilibrium and distort it, a rubber band or a wall or a steel beam or anything else, then it will exert a force that is proportional to the amount of displacement. This constant here is called the spring constant. And for example, we might measure this in the laboratory by saying, let's suppose we take the system, the spring or rubber band, and stretch the system out here a distance of 4 meters. And when we bring it out to a position of 4 meters, we experience a force of 12 newtons. If we do that, then you can see that 12 newtons is going to be equal to minus k, or let's just say k, times our distance 4. And so therefore k is going to be equal to, we can forget the minus sign here, the magnitude of k is going to be equal to 12 over 4, or 3. And therefore, anytime we distort by any other distance, we can put k is equal to 3 in this equation and get the force for any amount of distortion. Now, you can ask the question, why does this arise? Where does this really come from? And we can show that this comes from the fact that this actually has a potential energy associated with 1/2 kx squared. Let me show you how that arises. If we look at the potential energy, then the potential energy of a system is going to be equal to the force times the distance, integrated from 0 out to a distance x, let's say. This is the potential energy, or we could call it the potential. Let's call it V. V would be a function of x then. And so when we plug that in, we get the integral from 0 to x of the force, which is minus k, and the minus k will come out front, times x dx. Now, we're going to have to push in the opposite direction, so actually the force that we're pushing with is going to be plus. Because the spring is exerting the negative force, we're going to have to exert a positive force to overcome that, to stretch the spring out. For example, if you're using a Bowflex or something like that, and you stretch this thing out, the spring is pulling back with minus kx, but you're going to push with an equal and opposite force plus kx. So I put in plus kx here. Now we know how to do the integral of x dx, and that's going to be equal to 1/2 k times x squared. Evaluated between x and 0. So if I evaluated at 0, I get nothing. Evaluated at x, I get this. So we conclude that the potential energy, V of x, is equal to 1/2 k x squared. This is how much energy is stored in a spring. The energy stored is equal to the work it takes to stretch it out there. And you'll notice here that if you're doing exercises with some type of spring device, and of course you see these sold on television all the time, some type of spring that you're supposed to elastically pull out here, you'll notice that if somebody pulls it only half the distance, they're only doing 1/4 the work. So you can pull this a short distance and you're not doing much work at all. You have stored very little energy in it and you have done very little. If you push it twice as far, you'll do 4 times the work because it depends upon x squared. If you do 4 times the distance, then you do 16 times as much each time. So these are the two critical equations that we have: the force and the amount of energy that we store in the spring. Now we could go back up here to this problem where we computed what K was and say, okay, for this spring, how much energy did we store when we moved it out to this distance? Well, we noticed that we had a force of 12 newtons, we had a distance of 4 meters, and we had a K that's equal to 3 that we computed. Well, knowing this, knowing the position and the spring constant, we can now compute the energy that we expended in, or the work that we did in stretching the spring out to that point, and therefore it's the energy that's stored in the system. This is a conservative force, and we're going to lose none to heat. So therefore we can say that the potential energy, or V, at the distance of 4 is going to be 1/2 times K, which is 3, times x squared, which is 4 squared. 4 times 4 is 16, half of that is 8, 3 times 8 is 24. So it was 24 joules was the amount of work we did, and it's 24 joules that's now stored in the system. So in any elastic system, we can store energy in it, we do work to perform that deformation, and the deformation gives us a force given by this equation, which is called Hooke's law. The operable things to know here is that this is called Hooke's law. The force is proportional to the distance. It's in the opposite direction from the deformation. Secondly, this will hold for essentially any deformation near equilibrium. The constant is called the spring constant. And if we know the force and we know the distance, we can compute the spring constant. And that's normally how that would be done first. Knowing that, for any deformation, we can compute how much work it takes to do the deformation, and therefore the amount of energy that would be stored in the system, in this case 24 joules. Where does this come from? I'm going to show you how we can take that and expand a Taylor series expansion and obtain that result. Okay, this comes from the fact that we can write our V of x. This is the potential energy, and we can expand that in a Taylor series expansion about the equilibrium point, which I'm going to call 0. So expanding V of x using a Taylor series expansion, we get V of x plus dV dx evaluated at 0 times dx, times x, plus 1/2 the second derivative of V of x with respect to x, evaluated at the point 0 again, times x squared, plus, and as you know, the other sequences here would be continuing in that same sequence with the Taylor series expansion, but we don't need any of these higher terms. You recall that the force is minus the derivative of the potential with respect to position, often written as a partial derivative if you're familiar with partial derivatives yet. So the force is given by this formula here. So if I know the potential energy, I can take its derivative with a negative sign, and that will give me the force. Well, now, if I look at this potential, this is a potential at 0, and we can set this to be 0. How can we do that? Well, that's just the potential at a reference point. It's a constant, and it does not influence the force at all. Since it's a constant, it will not affect this derivative. The next thing is we can look at what is dV dx at the point 0. Well, dV dx is going to vanish at the point 0. This has nothing to do with the x here. It's the term in front. This is equal to 0 because the system is in equilibrium at that point. If it's in equilibrium at that point, then we're basically saying dV dx would be the force, but there's no force at the exact center. Therefore, this term vanishes. That leaves this term here. This term here is a constant. We're going to call this constant k, and so what we end up with is v of x to lowest order approximation is equal to 1/2 k times x squared. Well, that gives us our potential. You can say, well, that's what we've already derived. Yes, it is, but now we're going to turn around and take that and compute what the force is. The force is the negative of the derivative of that. So the force for this is describing any system near equilibrium now. Remember, this describes anything. If I take the negative of the derivative with respect to x, then I'm going to end up with a minus 1/2 k. The derivative of x squared is going to be 2x, and that's it. The 2 cancels with the 1/2, and I end up with a force that's equal to minus k times x. So I have derived this equation up here. I've also derived this equation here, and I've done it with very general principles based upon the fact that the potential at equilibrium is going to give me no force because it's at equilibrium, and the potential that's constant can always be set equal to 0, so that to the lowest order approximation for any elastic system, we can be assured that Hooke's law will be applicable, where the force is the negative of a constant times the distortion, and the energy is given by this equation here. So we have two things to remember, this one and this one. That shows this worked out in red here, where we've canceled those first two terms.